Okay, welcome to the last day here, I guess, besides the final, but last day. Um, so we sort of finished up the last chapter yesterday, what we're going to cover, obviously, out of that. And so we're just going to maybe do some reviewing here today. Is there anything specific anybody wants to talk, or I was just going to kind of go through the chapters, maybe highlight, obviously, the stuff. We'll start with that. Anything specific anybody like to talk about? Okay, then I'll just kind of start from the beginning. We'll see how far we get, kind of recall what was in those chapters, and I'm gonna look at the notes myself to remind me what was in those chapters. All right. So we'll start way back when, 8 weeks ago, maybe. Chapter 1 here. So chapter 1, obviously, we started talking about atoms, and we jumped kind of right into atoms. So after we got through some of the basic stuff about scientific method, we got into really our atom, which obviously, as we talked about, has protons, electrons, and neutrons. And we talked really about several sort of experiments that sort of led to the discovery of the atom, to highlight some of those. And obviously before that, our good friend Dalton, right, and his atomic theory, which basically sort of summarized the idea of what an atom is. And as we talked about, there are a couple of points to Dalton's atomic theory that are not really correct. The idea that atoms of the same element are the same. So all atoms of the same element are the same. And again, that is not so correct. Again, the existence of isotopes, as we talked about, are the same elements, but obviously they have different masses. So that is sort of the idea that atoms are indestructible is another one that sort of is incorrect as well. Remember that sort of the atom and all of its sort of beginning look at these three sort of subatomic particles really started with electrons. And really, it was the CRT tube, right? The cathode ray tube that was used in some experiments to help us understand really the nature of electrons. And really, Thomson did a lot of work, and Milligan were two sort of experiments that we talked about. Thomson did really the CRT, Milligan did the oil drop experiment. And remember that really the outcome of sort of both of those experiments was the idea of the mass of an electron. And we know electrons sort of had a negative charge, and really the mass of an electron sort of came out of that experiment. That also led to really sort of the first, or really one of the main sort of models of the atom, which was an early model, which was done by Thomson, and that was the plum pudding model. And if you remember, sort of the plum pudding model of the atom was that the atom was basically a sphere, and it had positive charge spread out through it. Electrons were embedded inside, and most of the mass of the atom was those electrons. So this was, again, sort of an early model that came out of those sort of idea of the experiments done by Thomson and Milligan and some others using the CRT tube to sort of explore electrons. It was also believed, obviously, and why sort of this model came about was, the idea that the atom was electrically neutral. So they knew it had negatively charged electrons. So this idea of really the positive charge being spread out all over it sort of came from this model. It was sort of the accepted model of the atom until we had really the next sort of major experiment that we talked about, which was our friend Rutherford. And Rutherford did the gold foil experiment. And remember that the idea was based on the plum pudding model of the atom, that when he shot alpha particles at it, which are heavy, positively charged particles, he did expect these alpha particles to sort of go through with deflection as you're shooting again something that's positive at something that's positive. Remember, things that have the same charge don't like to be near each other. And they were really surprised that when they did shoot these alpha particles, they found that really, most of them went through with no problem. every now and then these alpha particles, right, were basically scattered at these really large angles. And as we talked about, what that meant was it really did have to hit something that was very, very densely positive, which obviously meant that our plum pudding model, as we talked about, had to be sort of revisited. And it really allowed them to come up with really the modernish version of the atom, where we have basically the atom is mostly empty space, which again accounts for why most of those alpha particles went through with no problem. It does have a dense positive core, which is our nucleus. And as later experiments showed and done, inside our nucleus is obviously our protons, which are positively charged, and our neutrons, which obviously have no charge. And out from the nucleus at some distance, again, traveling in sort of a random pattern, is our electrons. So that was a really big sort of experiment. It really did lead to a change in the understanding of the structure of an atom, and again, moved away from obviously the plum pudding model to this more modern model of the atom, and how electrons go. Any questions on that there? Let's see what else was in that chapter there. That actually, I think, led us into a talk of some important aspects of atoms like protons, electrons, and neutrons, and how to count those things. And we came up with several things like the atomic number. And the atomic number, right, is our number of protons there are in an atom. We also have the mass number, which is our number of protons and neutrons in an atom. Remember, out of the two, as we know, hopefully, right, it is only this one here that you can find on the periodic table. It's the atomic number, and it's really the important number because, again, no element repeats atomic number. So if you know the atomic number, which means you know the number of protons, as we talked about, you should know what element you are dealing with. Remember, the mass number is not found on the periodic table. Again, the number underneath the symbol there is your atomic mass and not your mass number. But you would have enough information to calculate the mass number, atomic number, protons, electrons, and neutrons in these type of problems as we talked about. The importance of all that and the way you can remember that is basically your atomic number, your mass number, and the number of protons, electrons, and neutrons are all whole numbers, right? And again, obviously the atomic mass there on the periodic table, not whole numbers, so that's the way to do it. We also talked about the idea of isotopes, and again, isotopes are really the same element, but has different mass. And the reason they have different masses is because they have different numbers of neutrons. Remember, they cannot have different numbers of protons, otherwise they will not be that element. So it is the number of neutrons that vary there that gives it different mass along the way. We do write these sort of guys in a couple different ways, but most commonly we use the symbol. And again, up on top is going to be our mass number. Up on the bottom left there, going to be our atomic number. And again, that is commonly how we do it. Another common way is sometimes they'll use a symbol and a number, and that is the mass number. Like copper 64, that means that is copper with a mass number of 64. Again, you know, if you had something like this, let's try that again with the hydrogen. There we go. Something like that would be something for, say, a hydrogen isotope there, and it would look something like that. We also talked about, I think there with this is the idea of ions, and when things do get charges, and as we talked about a number of times, obviously ions are things that have charges, and that is two types of ions that we come across, which are cations that are positive, and we have anions which are negatively charged. Ultimately, things become positively charged because they lose electrons, which means they have more protons than electrons. And things become negatively charged because they gain electrons because they have more electrons than protons. So this is usually a loss there of electrons and a gaining of electrons that occurs for those guys. When we do have something like that, again, the only thing that really does change versus say Na and Na plus, sodium here has 11 protons and 11 electrons to balance it out to give you a 0 charge. And our sodium here at the +1 charge will still have 11 protons, but it will have only 10 electrons that gives it the +1. So if something does gain a charge, remember that the only thing that changes is the number of electrons. Again, not the protons. Otherwise, obviously, you change the element along the way. Any questions on any of that stuff there? I think we also in that chapter, looking at it here, we touched just a little bit about energy towards the end of that chapter. And again, we talked about some important units of energy like joules, calories, and one that relationship that we did see in terms of energy throughout sort of the semester is that obviously besides the two things that we mainly talked about, which was exothermic and endothermic. Remember that again, a endothermic reaction, heat and energy is absorbed. Exothermic heat and energy is being released. And usually in terms of energy values, exothermic is a negative sort of energy value and positive value for endothermic as it's being absorbed. And one relationship, as I was talking about there, that we saw was a joule is a kilogram meters squared second squared. So that relationship we saw in a couple of formulas, I think, throughout the semester where that sort of substitution sort of occurs. Any questions on any of that stuff there from good old chapter 1, I think. Yeah. All right, let's take a look and see what's in chapter 2. All right, so in chapter 2, we got into a little bit more about electrons and really we started sort of this chapter talking about waves. And remember, waves are really movement of energy through space, and waves have a couple of different spots or things about them, like their wavelength, which is lambda. Also have the amplitude of a wave. We also have the frequency of a wave, which again is how often basically a wave passes a point in a second. And we have a couple of equations that we saw in terms of waves that sort of move energy throughout. And that is C is equal to the wavelength times the frequency. So that is our speed of light. And that is a constant, which is our 3 × 10⁸ meters per second. That is our wavelength, which is usually in meters, and that is our frequency, right, which is in reciprocal seconds. A reminder as well, a reciprocal second is the same as a hertz, right? So a hertz is another unit of frequency that is used, and they are basically related to each other. A lot of what we talked about in terms of waves in this chapter is the idea of electrons sort of transitioning from, say, lower energy level to higher energy level, and then working their way back. The idea of sort of the conservation of energy is there's a certain amount of energy either given off or released from the atom as this process is occurring, depending on which way it goes. And a lot of times that energy is released in the form of a wave with a specific wavelength. We also saw a relationship that you could calculate the energy of these things by energy is equal to h times the frequency, h being Planck's constant, which is our 6.63 × 10⁻34 joule seconds. And that again is our frequency in reciprocal seconds. And that gives you an energy of joules. Because C is equal to the wavelength times the frequency, we could rearrange that equation and solve for the frequency, which would be C divided by the wavelength, which means we could actually insert that into that equation. And we could see that we could actually calculate the energy of a wave by just knowing the wavelength. You could also obviously calculate the energy of a wave there by knowing the frequency. So it allows you to do obviously either one in those cases. by doing that sort of calculation. And obviously you could use the speed of light there to get between any of those things. The idea of our electrons sort of transitioning led us to the idea and a little talk as well about the electromagnetic spectrum, right? And here we have different sort of areas of the spectrum. You got like radio waves, microwaves, right? You got some visible rays, you got some X-rays. Not all of them are written up here on my chart here. We have gamma rays. We also have UV and stuff like that, and visible in there as well. But really, as we were talking about, sort of these electrons sort of transitioning from one energy level to the next, as they give off that energy in the form of a wave, it will perhaps correspond to somewhere in the spectrum. And it may even correspond in the visible part of the spectrum, right? And that is where we see our colors, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. And depending on sort of where it falls as to maybe what we would see or what we may not see, obviously if it falls in the visible part of the spectrum, we will see some color. We did a couple experiments, right? Flame test. We used a spectroscope, right, to sort of look at those type of things. And depending on where it falls outside of that, you may not see that. There is a relationship, right, between basically the wavelength, the energy, and the frequency. So if you have a wavelength such as this versus a wavelength such as this, right? When we have a much smaller wavelength, we usually have a much higher frequency, and that usually is consistent with a higher energy, and vice versa here, where we have the longer wavelength, we have the lower frequency, I guess is a way to put it, and usually the lower energy associated with that. And we see that difference even with the visible part of the spectrum where we see colors. Usually in the visible part of the spectrum, those guys are read often nanometers. And even with the colors, we do see that red being a little longer of a wavelength, and kind of near the purple side there, the violet being a much shorter wavelength, which is higher in energy. And depending on the colors that we see, for example, when things transition, it also tells us maybe how many energy levels it is transitioning. So something transitions a lot of energy levels, it will have higher energy and a lower wavelength, and vice versa in terms of that. So in terms of our electromagnetic spectrum, this side is really our kind of shorter wavelength. And this side, I'm sorry, I wrote that backwards, longer wavelength on that side. And that guy is shorter on this side. And obviously towards our gamma is very high in energy. It's really just pure energy. Obviously radio waves, not so bad in terms of energy. But obviously as you progress down that spectrum, the energy sort of increases. Any questions on that wave there stuff? I think we also talked about in relationship to our electrons transitioning, that you could calculate the change in energy that occurs by taking 2.18 times 10 to the minus 18 joules, which is Rydberg's constant, 1 over n squared final minus 1 over n squared initial. And our n is our energy levels that basically occur here, and that should be a negative there. These are our energy levels. So basically the final energy level of the electron minus the initial, and this will give you the energy associated with that transition of an electron from one energy level to the next. We also could tie in all the other energy equations that we saw, which is our h times our frequency, our hc over our wavelength. So we could tie obviously all those guys in together. So in addition to figuring out, as this electron transfers sort of energy, our levels, you can figure out the wavelength of, for example, that wave. You can figure out the frequency of that wave by tying those guys together. N is really the principal quantum number. And again, that's really just a fancy name there for our energy level. So as we were talking about this stuff, we were talking about the idea of this sort of quantized energy that is released as electrons go in this more quantum mechanical sort of model of the atom, and the idea that waves possess both a wave-like character and also particle-like functions that occur there. We also had de Broglie and his wavelength, which basically was the idea of sort of a standing wave like on a guitar string. That the electrons, although they are moving, they are sort of tied to the nucleus, right? Because of that attraction force between the positive and negatives. And both a particle can have a wave-like function and a wave could have particle-like function. And we talked about calculating the de Broglie wavelength as well. Ultimately, though, towards the middle of this chapter, we moved away from the idea of orbits, like we saw in Bohr's model of the atom. And in Bohr's model of the atom, remember, is more of that planetary sort of model where, you know, we have these electrons in these orbits as they're moving around, like, you know, n equals 1, n equals 2, and so forth. And this idea of sort of quantized energy, that electron really can only transfer from one energy level to the next and won't find itself in the middle or anything like that, is sort of an idea that came about. And remember that we talked about sort of the idea of staircase and energy and quantized energy. Again, you'll either be on this step, or this step. You usually, again, will not find yourself in the middle. And that's basically how electrons basically transfer from one energy level to the next. They gain or lose enough energy to make it from the one energy level they started at to the next. Again, they don't basically find themselves in the middle. And that's different than sort of continuous energy, where we sort of talked about it as a ramp. If you're walking up a ramp, again, you can pretty much stop anywhere you like along the ramp. And that's more of a continuous sort of spectrum. Continuous spectrum is something that we see where like everything sort of comes out at once. And that's like on the sun, for example, we get everything sort of happening at once. But atoms and stuff like that, and those type of elements basically are more of a quantized sort of situation. And that led us to really the type of spectrum that we see with elements, which is a line spectrum. And like that experiment that we did in a line spectrum, because these are sort of quantized, what we see is specific lines that happen at specific wavelengths that have specific colors. They're so specific for elements that you can look at a spectrum, and depending on what lines you see and at what wavelengths they break out at, you can determine what element you're looking at. So every element has its own sort of line spectrum. And again, that was look like that spectroscope experiment we did, where we looked at and you saw all the different lines at the different wavelengths. Now, as we moved away from this Bohr model with the idea of things like the Heisenberg uncertainty principle and Schrodinger's equations, these are ideas that there's no good way to know exactly how a particle like an electron is moving. And in fact, the more that you know about the location of a particle like an electron, the less you know about how it's moving or traveling, and vice versa. And that moved us away from this idea of orbits to this idea of orbitals. And orbitals are these sort of theoretical mathematical descriptions of where we find electrons in the atom. And there's s orbitals, there's p orbitals, there are d orbitals, there are f orbitals. And any individual orbital can hold basically 2 electrons maximum. And in terms of s orbitals, there's basically one type. In terms of p orbitals, there are 3 types. D orbitals, there are 5 types. And f orbitals, there are 7 types. And when we talk about p orbitals, d orbitals, or f orbitals, or groups of p, d, and f orbitals, those are what are sometimes referred to as subshells or sublevels. And that means that really we would max out in terms of electrons 2 for our s. We would have 6 if we filled up the entire subshell there for p's. We would have 10 if we filled up the entire subshell for d's, and we would have 14 electrons if we filled up the entire subshell for the f's. We also talked about really the basis of why we see sort of these orbitals and on certain energy levels, and maybe why we don't see them and how many we see them. And that's really based on the idea of quantum numbers. And we talked about quantum numbers, and there's really sort of 4 quantum numbers that we talked about. There is n, which is our principal quantum number. Again, that's basically the energy level. And n could have values of like 1 through 7. L is our angular momentum, angular quantum number, and L could have values of 0 to n minus 1. And this sort of tells you the type of orbital that you're dealing with. Is it a s orbital? Is it a p orbital? Is it a d orbital? So for example, again, if our n is equal to 2, that would mean we're on the second energy level. We could have values of L that goes from 0 to 2 minus 1, which would be 1. And in this case, a L value of 0 represents an s orbital. A L value of 1 represents basically a p orbital, and so forth. Obviously, a 2 would be a D, and a 3 would be an F. And as we talked about, it goes sort of alphabetical at that point if you get higher than that. We also have M sub L, which is a magnetic quantum number there, and that goes from minus L to 0 to plus L. And this really tells you the orientation in 3-dimensional space of these orbitals. It also tells you how many orbitals you have. So for example, for each of these L values, you could have an M sub L value, which in this case would be 0. For this guy, our M sub L values would run from minus 1 to 0 to plus 1. Here, there's only one M sub L value, which is an s orbital, and there's only one type of s orbital. Here, we actually have 3 M sub L values, and those represent the 3 p orbitals that there are in every p subshell. And this is like px, py, and the pz orbital. Each of those numbers basically represent. And there's also the spin quantum number, which is m sub s, and that has a value of plus or minus 1/2. And that is related to, obviously, the way that the electrons are placed into the orbital, which sort of direction they're heading. Remember that really the first one that gets sort of placed into the orbital usually goes in the upward spin direction, and that is positive 1/2, while the second one that goes in there, and I'll just draw it in a different one, heading in the opposite direction there, we'll put one together, is minus 1/2 here when you put it back in there. So these sort of quantum numbers is really why we see, for example, that on the first energy level, there is only an s orbital, because again, n is equal to 1, which means L would equal 0, and M sub L would equal 0, and M sub S would equal plus or minus 1/2. That means really on that first energy level, all we see is basically an s orbital. Again, as we just did up here with our n equals 2, it's not until the second energy level that we start to see those p orbitals occur. When we get to the third energy level, L would have values of 0, 1, and 2. So we have our s's there, our p's, and our d's. So it's not until the third energy level that we get our d orbitals. And obviously, if you did n equals 4, and we won't go all the way through each of these, but n equals 4, 0, 1, 2, and now 3, and that is where we start to see our f orbitals basically start to occur. So this is really sort of the basis behind sort of quantum mechanical model of electrons, and also the basis behind electron configuration and the order and where we put electrons in there. And this is also this idea of remembering that we basically just have an s orbital on the first, a p orbital is where we start to see on the second, d and f. Allows you to really write or make the correct order for electron configuration. And you can do that by really just doing that. On the first energy level, there's an S. On the second, there's a P. On the third, there's a D. And on the fourth, there's an F. And basically just fill in the numbers underneath. So that would be 2S, 3S, 4S, 5S, 6S, 7s, 3p, 4p, 5p, 6p, 7p, 4d, 5d, 6d, and 5f. And remember that this is really the order at which electrons are placed into the atom. And there is some differences in sort of what you would expect if you know this. And again, as we talked about a second ago, 2 electrons for the S's, 6 for the P subshell, 10 for the D subshell, and 14 there for our F subshell. You really should be able to write any electron configuration that you would need. As we talked about, the main sort of difference happens here as we go from, say, 3p to 4s back to 3d. Again, what happens when electrons get filled into the atom, which is how we write electron configuration, all the S's really end up being lower in energy than the D's. And that means that they actually do receive the electrons first, followed by the D orbitals, not to be confused with something we talked about afterwards, which is after they start putting electrons into D orbitals, there is that switch in energy that occurs, and the 4s actually ends up being higher. But in the filling order and how you write electron configuration, the S's always come first there before the D's. That gives us something like, 1s2, 2s2, 2p4, for example. And we could write our electron configuration. Obviously, we could just count the top there, and that's 4, 6, 8. So that obviously is oxygen's electron configuration that we just wrote there. That is the way to write it. We also can represent this by what is referred to as the orbital diagram that we talked about. The orbital diagram is basically either boxes or lines, and you'll have a box for a 1s, a 2s, and here we would have 3 boxes or 3 lines for our 2p. Remember, again, electrons go in up, down, and here they would go in up first, right? Maximizing parallel spin, which is Hund's rule, coming back and then pairing off. We also can write the electron or the 4 quantum numbers for any of these sort of guys as well. So you could pick an electron and actually write the 4 quantum numbers. Here, n would equal 1 because that is 1. L would equal 0. M sub L would also equal 0. And here, because it is pointing upwards, M sub S would be plus 1/2. So we can do the quantum numbers for any of the electrons that is in there in a particular electron configuration. We also talked about, obviously, there's some shorthand that you could use for electron configuration, and that is using a noble gas. So you could do something like 1s2, 2s2, 2p6, say 3s1. When we take up to here, that is 10 electrons, which is neon's configuration. So you could put neon in brackets and continue on that way. And that is sometimes referred to as noble gas configuration. And it has to be a noble gas, obviously, that goes in the bracket, and you just continue on with the electron configuration at that point. Any questions on that there? We also talked about, obviously, when we do have something that has a charge. So as we talked about earlier, it is just the electrons that change. So if something does have a charge, you do need to adjust the electron configuration. So if we did have our sodium with a +1 charge, instead of 11 electrons, it actually would have 10 electrons, which means its electron configuration 1s2, 2s2, 2p6, or that is neon's configuration, would be what would happen in that particular case. And that also means that neon, for example, and sodium with a +1 charge are isoelectronic with each other. Isoelectronic means 2 things that have the same electron configuration, and that happens with all representative elements. So representative elements are our elements that are not transition metals. Most representative elements, they will either lose electrons, which is what happened with metals, and that allows them to back up to the noble gas that comes before them, like sodium. Non-metals, like say oxygen, will gain electrons and go forward on the periodic table, say to neon, and that will also allow them to have the same sort of electron configuration as the noble gases. as we talked about, that is really the basis of all bonding. Is for that to happen, everybody gets the same electron configuration as the noble gases. And that's how really representative elements do it. They gain and lose electrons to reach that noble gas configuration. The exception, as we talked about, there are a couple exceptions. There's a lot of exceptions in terms of normal electron configuration. The two that you're responsible for to know is chromium, which is 24, and copper, which is 29. And the main sort of exception that both of these have is when you get to the S. Actually, only has one electron in the S. The other electron has been moved up to the D. I'll just write right here, the d orbitals. And in the case of chromium, you'll have 3d5 at the end. And in the case of have your 4s1, 3d5 sort of happening. And in the case of copper, you'll have your 4s1, 3d10 happening. And they have one extra electron up there in the d orbitals. And that's obviously the end of the configuration as to where you see that. And it makes them more stable. We also saw some others, and you're not responsible for them. But again, pretty much if you look where chromium copper is on the periodic table, you go below them and kind of inward. There's a lot of exceptions like that. Like PD has, I think, no electrons there in the D or in the S. They've all been uploaded there to the D. They could do that because they are really close in energy to begin with. The S and the D orbitals. So as they are filling, for example, they are super close in energy. And as they start to put electrons in, there's actually a switch in terms of the energy. And what ends up happening is, in this case, the S ends up being a little bit higher in energy. And really where that comes into play is when they go to lose electrons. And these are really transition metals, is really where our d orbitals start. And in transition metals, because this occurs, when they lose electrons, they will actually lose their S's first. So unlike when you look at the electron configuration for representative elements, it's really just the last stuff there. That's where those electrons sort of come out. Here, it's really going to be those S's that are always lost first. So if we had something like iron that had a +2 charge, and iron is 26 with no charge. So with a +2 charge, this guy would have 24 electrons, and we would have something like argon 4s2 3d6, and that would be iron with no charge. So when it goes to 24, it will lose these 2 electrons here, and that will leave us something like argon 3d6 for our iron with our +2 charge in that case. If it needs to lose more electrons, at that point, it would go into the d orbitals next. So if we had to go to iron with a +3 charge, we would then have no choice but to take it out of there, and we go down to 3d5. So transition metals are really different in that aspect. They will lose those s electrons first because there is that switch in energy that occurs, and they end up actually being higher in energy. Typically speaking, when we talk about electrons, there's 2 types of electrons. There are core electrons, which are closer to the nucleus, and there are valence electrons, and those are higher energy electrons. And it's really the valence electrons that are involved in bonding. Those are the most important ones. They're involved in bonding because they are further away from the nucleus. They're not held as tightly. They're easily removed or shared, rather than core electrons, which are much closer to the nucleus and held a lot tighter. Any questions on that there? You also can really just look at the periodic table, and if you kind of know what you're doing, you can count off electron configuration just by sort of looking at the periodic table. And speaking of the periodic table, we also talked about in this chapter, we have groups, right, which are up and down on the periodic table. And remember that periods head this way, right? Periods. And there are 7 periods on the periodic table. And we have some special group names. That is our alkali metals. That's our alkaline earth metals. That is our halogens. That is our noble gases, right? We also have a staircase that kind of comes down there from boron, which is over here. And to sort of the left there is our metals, right, which are good conductors of heat and electricity. Above this staircase there are our non-metals. And on the staircase there, as you kind of come down in twos for most part of it, are our semi-metals. So non-metals are bad conductors of heat and electricity. They're dull, they're brittle. Semi-metals are guys that have basically properties that fall on both sides. Some that are very metal-like properties, some that are non-metal-like properties. And obviously we have our 2 rows down here. That's our lanthanides and actinides series. And remember that those, if you follow the numbering, go right about there on the periodic table when you look at it. We also have transition metals, which are here between groups 2 and 3 on the periodic table. And really, because these 2 on the bottom technically do go in that spot, they're sometimes referred to as intertransition metals because they kind of go in the middle there. Now, this is the periodic table, and then obviously a couple of things from the periodic table that we can get information from. We can obviously get the atomic number, which is the number of protons that you can get for each element. We could also figure out the number of valence electrons, and that is equal to the group number. So the number of valence electrons you could get by writing the electron configuration, or you could just go over the group number. Everybody in group 1 has 1, everybody in group 2 has 2, 3, 4, 5, all the way across there. Other things that we could get, as I mentioned before, there is electron configuration. You can sort of count yourself or count the electron configuration by using the periods as the n number. That's why there's 7 of them. But remember the first 2 groups here, that's your S block on the periodic table. 3 through 8 is your P block in terms of electron configuration. Your transition metals is your D block, where D's happen, and your kind of lanthanides and actinides are your F block down here. Remember that there's a couple things that you really have to be aware of, and the first major one is not drawn to scale here, but really the transition metals start down this way, and although they are on period 4, which means n would equal 4, the first one's actually 3D, so that would be 3D, not 4D. And same thing down here, although these guys technically would go here, they're actually 2 behind the period number. So instead of being on period 6 where they technically should go, this is actually 4F, so they're 2 behind the period number. So there is some places, if you try to count it off the periodic table, it can get a little messy if you're not thinking about sort of what's going on there. But if you, for most things, you could really just count the boxes and you'd be able to get the electron configuration. Any questions on that stuff there? Let's see. There's a lot of stuff in that chapter. What else we got in that chapter there? So I think we, in addition, obviously, talked about the periodic table. We talked about some periodic trends, I think, at the end of that chapter. And we talked about some of these periodic trends. And we had things like, just drawing the generic periodic table. We saw that atomic size gets smaller, right? Decreases as you go up and to the right, and increases as you go down to the left. We also saw ionization energy. Increases as you go up and to the right, and decreases. Remember that ionization energy is the energy required to remove an electron in the gas phase. We also saw electron affinity increase generally increase as you go up and to the right and decrease as you go down. Electron affinity is really the energy change that occurs when an atom gains an electron. And that is not to be confused with electronegativity, which is different than electron affinity. And electronegativity increases as you go up and to the right, decreases as you go down, although not in the right spot, but obviously way up here. Fluorine, right, is the most electronegative element that we have. And electron affinity is the ability, electronegativity is the ability of an atom to bring electrons towards itself, right? So it's the process of bringing electrons towards itself. Electron affinity is the actual energy change that occurs when an electron is actually gained by an atom. So when we talk about electron affinity, we usually talk about anion formation, right? Things that become negative. When we talk about ionization energy, we talk about basically cation formation. That's when they lose electrons. Electrons, in terms of ionization energy, as we talked about, occur basically one at a time. So something loses an electron one at a time. And that's how we get first ionization energy, second ionization energy, third, and so forth. That represents the energy required to remove each individual electron. As we talked about, it gets harder and harder to do that. So every time you rip off an electron, the overall size of the atom gets smaller, which means the outer electrons now are closer to the nucleus, and they're going to be held a lot tighter, so it takes more energy to do that. So the general trend that we see in terms of first ionization energy to second to third is that it starts to increase every time you rip it off. And at some point, like we saw in that table, if you remember, you get yourself into those core electrons, and it's a tremendous jump in energy, and it doesn't usually happen under normal conditions. And that's why certain things like, say, sodium, which has one valence electron, will only make a +1 charge, because the jump in energy to try to rip off that core electron after you got rid of the valence electron is just too much, and it doesn't happen. So it sticks with that +1 sort of situation. All these things, as we talked about in terms of periodic trends, these all lead to what we know hopefully happens. Everybody in the upper right of the periodic table, which is our nonmetals, they have all these trends that make them want to hold on to their electrons, take other people's electrons, and not let go of theirs. So this is these guys that like to gain electrons heading this way. These are all guys that frankly don't care that much about hanging on to their electrons. It doesn't take a lot of energy to remove their electrons. So these are our metals, which typically will lose electrons because of these periodic trends. And any questions on any of that there? I think that's everything out of chapter 2. That's about chapter 2. All right. Then we rolled into everybody's favorite, which is chapter 3. Speaking of a lot of stuff in there. We basically covered bonding in this chapter, and we talked about 2 different types of bonding. We talked about ionic bonding, which is always between a metal and a nonmetal. And what happens in ionic bonding is we get the transfer of electrons happening. The result of that is we will create a cation from the metal, which is positive. We will create an anion from the nonmetal, which is negative. And it is that attractive force, that electrostatic attraction between the two, that hold them together. There is no sharing of electrons here. So positive, negative attraction. We were able to represent this type of bonding using Lewis dot symbols, are just electron dot symbols, and these are basically the symbol and 1 dot to represent each of the valence electrons that are present. Remember, there's no real hard rule other than you got 8 basically total, and usually 2 on a side. And again, we could get the valence electrons from the periodic table and the group number. So if we looked at really the sort of formation there of sodium and chloride, we have our sodium ion that has 1 valence electron. We have our chlorine that has 7 because it's group 7. Remember that sodium basically has an electron configuration of neon 3s1. That is the valence electron. Chlorine is going to be neon 3s2 3p5, and that is the 7 valence electrons that we're looking at in terms of chlorine. What happens here is the sodium will transfer over its electron to the chlorine. The result of that is at that point sodium becomes plus charge. Our chlorine will pick up that electron and become negative charge. Remember that when you draw these type of things that are ionic, you should have the charges and maybe some brackets around some things. And what happens in electron configuration, sodium ends up in neon's configuration. And by gaining that electron, that's going to allow chlorine to go forward to argon's configuration. And as we talked about, that is the whole basis of bonding, is for everybody to achieve noble gas configuration, because they're going to be stable in that sense. And in the case of ionic compounds, that's exactly how they do it. Metals lose electrons, nonmetals gain electrons, allows both of the elements, or however many elements there may be there, or atoms, to all reach noble gas configuration, which is again really, really stable. Sometimes you may need more than one, right? Obviously, metal or non-metal to balance out the charge. Remember that whenever we have an ionic compound, all the positive and negative charges do need to balance out to 0 in the simplest way possible. And the reason for that really is really the bonding reason, because when you balance it out in the simplest way possible, that gets everybody to that noble gas configuration, and everybody will be really happy in that situation. The other type of sort of bonding that we talked about in that chapter, besides ionic bonding, is covalent bonding. And covalent bonding is a little different than ionic bonding. Covalent bonding is usually between two nonmetals, and the difference here is that we are going to share electrons. So there's some type of sharing of electrons that's happening here, and there's really two types of sharing that occur. There is equal sharing, which is what is referred to as a nonpolar covalent bond, and there's unequal sharing, which is basically a polar covalent bond. And there is some aspect of sharing that always occurs in a covalent bond. And the way that we can determine what type of bond that we really are going to sort of have is we could use the electronegativity values to help us. So if you remember in this chapter, the actual more electronegativity conversation revolved around Pauling's sort of values of 0 to 4 for all the elements. The most electronegative and obviously the least electronegative there. And we could do the change in electronegativity values by simply just subtracting the two values. So carbon at 2.5 and hydrogen at 2.1. We just basically take the difference, and you just take the larger number minus the smaller, so you get a positive number, and you get a difference basically of like 0.4. And there is sort of some breakdowns in terms of what's considered nonpolar, equal sharing, and what's considered polar. Anywhere typically from 0 to 0.4 is considered nonpolar or equal sharing. Remember that a difference in electronegativity value of 0 means that you have perfect equal sharing, and that is also a nonpolar bond, but it is sometimes referred to as a pure covalent bond, where you have that sort of perfect equal sharing. Anything really above 0.4 to below 2 is a polar bond, which means we're going to have some type of unequal sharing of those electrons. And not in all cases, but typically anything above 2 is your ionic bond. Remember that you really do not need necessarily the electronegativity values to determine ionic bond. As soon as you see metal and non-metal, it's ionic. You don't need the values. Remember also, when you look at the periodic table, there's a couple of things in terms of electronegativity that's helpful for you, and also cases where you may not need the actual values. If you're comparing anybody like in a same period, it probably will be a polar bond because the person farther to the right would be more electronegative. If you're also comparing anything that's in the same group, you also really don't need the values because that also will lead to a polar bond because, again, higher on the list will be more electronegative, lower on the group there will be less electronegative. So in a lot of cases, you don't necessarily need the values. You can make a pretty good guess as to polarity, especially if they're in the same period or same group. There's also that diagonal relationship that we talked about, which sometimes can come across, where you can get, two elements that are diagonal of each other. Maybe not directly diagonal, but kind of down and over one diagonal sort of situation, like carbon and sulfur. When you look at periodic table, carbon and sulfur have the same electronegativity values, and that's because carbon's further up, but sulfur is further to the right, and they're only like one away from each other in terms of periods. So they sort of cancel out their differences. So it is definitely potentially possible to have two different elements that actually will be nonpolar. But in a lot of cases, if you have two different elements, they probably will be polar, but that diagonal relationship is there that sort of cancel each other out. Any questions on that there? Now, this led us into really talking about sort of the good way or proper way to draw Lewis structures for covalent bonding. And when we do Lewis structures for covalent bonding, we do follow some different sort of rules to help us get to hopefully the right sort of thing. So for covalent guys and Lewis structures, there's some important things that we want to do. We want to really count the total number of valence electrons. And remember that if you do have a charge, positive or negative, you do need to include that charge into your overall count. Otherwise, you're going to be short or not have enough electrons. Again, if something has a negative charge, you need to add electrons to your overall count. Something has a positive charge, you need to obviously subtract electrons to your count. Now, the next thing that you want to do is sort of the logical arrangement of the atoms. And usually in the center position is the least electronegative atom. So the least electronegative atom is usually in the middle. We never find hydrogen or fluorine in the middle. Hydrogen, because it can only have 2 electrons, which means if it's in the middle, it's going to have more. And fluorine is the most electronegative atom, so it won't be in the middle. So it should always be on the outside. That also brought us to an important rule we also talked about, which is the octet rule, right? So everybody continues to make bonds till they have 8 electrons around them, except for hydrogen that only needs 2. Once you have that arrangement, you want to make one covalent bond from the center to the outside atoms. Then you want to fill up outside atoms with pairs of dots until they have basically 8 electrons. If you still have electrons to distribute after you fill up all the outside ones, then you go to the center and you also put them on as dots as well. At that point, once you start filling in the center with dots, if you need to, you should be out of electrons. The last thing that you want to do is basically check that the octet rule is met. And really, if it is not, this is really where we want to make a double bond or a triple bond to try to fix that situation. Remember that we can't just add electrons, otherwise we'll have too many electrons. But we do want to make a double bond or a triple bond to try to fix it. You usually want to use up all your double bonds first and then kind of move to triple bond to fix that situation. So again, if we look at something like NF3, we would have 5 plus 3 times 7. So we got 26. So we would do our arrangement like this. Again, we would make one single bond to each of the outside ones. That is 2 electrons per line. 2, 4, 6 is used. So we have 20 more to go. 2, 4, 6, 8, 10, 12, 14, 16, 18, and then those last two would go there. At that point, I've used up all my electrons. Everybody has 8, so I'm good. Remember, again, you don't want to really double bond or triple bond out of the box. You want to kind of save that to fix any type of situation. Now, sometimes people maybe do want to double bond or triple bond, or maybe draw a different arrangement of how everybody comes together. And we did talk about one sort of aspect of bonding that helps us perhaps decide between maybe some different Lewis structures. And that is something known as formal charge that we talked about. And formal charge is really the charge the electrons, the atom would have if all the electrons were transferred. And that's really the number of valence electrons in the atom or element by itself, minus the number of non-bonding electrons, minus 1/2 the number of bonding electrons. So if we take our Lewis structure we just drew there, and we wanted to do the formal charge for nitrogen. Nitrogen normally has 5 valence electrons. In this case, it has 2 non-bonding electrons, minus 1/2 bonding, 2, 4, and 6. So that gives us 5 minus 2, which is 3, minus 3, which is 0. So the formal charge here on the nitrogen there would be 0. And again, obviously, you could get a minus sort of formal charge or a positive formal charge. And you could have a situation where you might want to double bond or not double bond a situation, a element that may be there. Remember that you can have exceptions to the octet rule, and that's sort of where we sort of get some of these situations where maybe you might want to look at something like formal charge. So some exceptions to the octet rule is a situation where we have an incomplete octet. That was the word I was looking for. And that has less than 8 electrons. And that is usually boron in a lot of cases, aluminum as well, as those guys that commonly could do that. There's a odd number of electrons, and that's where you end up with really a unpaired electron happening on there. And those are free radicals. And really the sort of exception that we saw the most is, and you see the most usually, is the expanded octet. And those are guys that could go above 8 electrons. And that happens as sulfur on the periodic table, to the left, to the right, and down. And that is because like where sulfur is on the periodic table, that is the 3rd period, which means n is equal to 3. And that is where we first start to see d orbitals appear. And because they have d orbitals available to them, they have places to stash the extra electrons in there. That also means, as we talked about, things in period 2, like nitrogen, oxygen, and so forth, cannot go over 8 ever because they don't have that ability. They don't have the d orbitals, so they can't go over that because of that situation. So that brought us to, I think we did a look at something like sulfate here, where, we could draw it like this, or perhaps we can double bond it up like this. And when we use formal charge to help us decide, what might be a better structure, the best sort of situation is where you kind of minimize the formal charge so everybody zeroes out. Is like the best situation. If not, where you could sort of minimize as much as possible in terms of the formal charges. Things with +2s, +3s, really large sort of formal charges is not really usually the best sort of structure that occurs. Also, if you have sort of equivalent formal charges on different structures, you would want to choose the one where the more negative formal charge ends up on the more electronegative element. So if we just kind of calculated our formal charges on these guys for our oxygens here, our single bonded oxygen, it would be 6 minus 6 minus 1/2 of 2, which gives us a -1. So all these guys here that are single bonded would be -1 all the way on all these. And if we did our double bonded oxygen, it would be 6 minus 4 minus 1/2 of 4, which gives us 0. So that would be 0 and 0. And if we did our S over here in this guy, that would be 6 minus 0 minus 1/2 of 8. That's going to give us a minus 2 plus 2 situation going on there. And that's going to give the S there a +2. And if we did the S on the guy on the right, that's going to be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12. That's going to give us a 0. So as we can see there, the guy on the right there, we really minimize the formal charge on the sulfur to 0 by double bonding it. It's able to do so because it can go over 8 because it's able to handle that. And actually the one on the right based on formal charge would be the better structure of the two. I think we also looked at like CO2 double bonded versus triple bonded and some other examples, but you can use formal charge to help you decide between two structures, which one is a better structure. Again, you don't have to use formal charge unless you're asked to like draw one that is based on formal charge as a better structure. But that is a lot of times what we can use formal charge. We also can have structures where we have more than one option as to where we could put the double bond, and that's resonance structures, right? So where we could actually draw an equivalent Lewis structure for something where you maybe have an option to move the double bond to one place or the next. And it's based on just really moving your double bond around to all the places that's possible. We talked about strength of bonds and bond length. And here, remember that basically a single bond, double bond, and triple bond, that is the weakest and the longest typically. And that is the strongest and the shortest. And really, when we kind of put on a bond, what happens is everybody really starts to move closer to each other. So as we go from a single bond to a double bond to a triple bond, everything's getting moved closer to one another, which makes them a much stronger bond. And last thing we did in this chapter, or one of the last things we did in this chapter, is the one place where we talked about energy and delta H based on bond energy. And remember that in a reaction, basically we're going to break all these bonds on our reactant side, and we're going to make all the bonds on the product side. Remember that when we break bonds, it's an endothermic process, positive. When we make bonds, it's an exothermic process, which is negative. So really, when we do delta H based on bond energy, we basically add up all the bonds we broke. And there's that table where you can look up like a carbon-carbon single bond is this much energy to break it, triple bond, and so forth. And we add it to all of the bonds that we make. Obviously, you turn this guy into a negative number. This guy is a positive number. And depending on if you get your delta H is positive, it's going to be an endothermic process, gaining energy, absorbing energy. Negative, it's going to be an exothermic process, which is releasing energy. Any questions on that stuff in that chapter there? So the next chapter, we talked about really geometry and molecular geometry, which is sort of a continuation of what we were talking about in this chapter as well. And in sort of chapter 4, there is all about sort of electron pair repulsion model, our geometry. And really, we talked about two types of geometry. We talked about electron pair geometry. And we talked about molecular geometry. And that's sometimes referred to as the shape. And really, when we draw a Lewis structure, we could use that Lewis structure that we drew to really figure out what the geometries of these things are. And there's really two things that you should kind of look at when we do geometry. It's always about the central atom. And in some cases, there may be more than one central atom, but in a lot of cases, it's just one sort of central atom. And really the two things that you want to count about the central atom is really the number of electron pairs and the number of bonds, right? And there is sort of two exceptions that we do when we're doing geometry and only geometry. And that is the idea that if you have a double bond or a triple bond, it counts as one electron pair and only one bond. So that's really the major thing when you're doing geometry and only geometry: double bonds, triple bonds, one electron pair, one bond. And the other thing is, obviously, if you have a resonance structure, you can basically do this geometry for each of them, and usually it'll come out the exact same geometry, regardless of what resonance structure that you sort of draw. So there's a lot of different sort of electron pair geometry and molecular geometries that we talked about. Some of them electron pairs and bonds, electron geometry, molecular geometry. Remember that the simplest one, if you have a diatomic molecule, it's always going to be linear. So if you only have two atoms together, the geometry is always linear. It doesn't matter if it's single bonded, double bonded, or triple bonded, it will always be linear. When you get to three or more atoms, you could count these. So for example, if you had two electron pairs and two bonds, that's going to be linear and linear for both names. If you have three electron pairs and three bonds, that's going to be trigonal planar and trigonal planar. Four electron pairs, that's going to be tetrahedral and tetrahedral. 5 electron pairs and 5 electron pairs is going to be triangular bipyramidal on both, actually. Six electron pairs and 6 electron pairs would be octahedral and octahedral. Now remember, these are our expanded octets, right? So our exception to the octet rule. And in this situation and all of these situations, there are no non-bonding electrons present. So when you draw your Lewis structure, you have no dots on the central atom. So whenever you have basically no dots on the central atom, both the electron pair geometry name and the molecular geometry name will be the same. Remember that it's only when you start to introduce the non-bonding electrons to the central atom that you start to get some differences in the name. And when you get the differences in names, actually the molecular geometry name that changes, and that is because there are 3 types of sort of situations that occur in terms of electrons being near each other. And that is, we could have bonding electrons near bonding electrons. We could have bonding electrons near non-bonding electrons. And we could have non-bonding electrons near non-bonding electrons. This is the worst in terms of electron-electron repulsion. They do not want to be near each other. This is sort of manageable in terms of that. And that's why we do start to see some different geometries when we start to introduce our non-bonding electrons. So just the electron pairs and number of bonds, and we'll just do a few of them here. Electron geometry, molecular geometry. So, if we had something like 3 electron pairs, but only 2 bonds, this is still going to be trigonal planar. But this would be our angular type of situation, like we had with like SO2 here. So we have 3 electron pairs. Again, the double bond counts as 1. Non-bond electron counts as 2, and our single bond counts as 3 electron pairs, and only 2 bonds. Single bond counts as 1, double bond counts as 1. So this angular. So because this guy is sort of missing the 3rd bond there that you see in a trigonal planar type situation, it gives it a little bit more room to move around. It's not tied to another atom as it's moving. It also is non-bonding electrons near bonding, so they're going to try to get away from each other. So as they're moving to get away from each other, again, the bonded atoms start to move in accordance, and we get these different geometries. You know, like we have 4 electron pairs and 3 bonds. That's going to be tetrahedral. And that's going to be our trigonal pyramid. We have 4 electron pairs and 2 bonds, which would be our tetrahedral, and our bent are V-shaped. And obviously for our expanded octet, we obviously have those as well. Things like T-shaped, right? We had linear. We have things like square pyramidal, square planar, and stuff like that. So our expanded octets obviously have them as well. So when we start to introduce those non-bonding electrons, and again, something like water is even worse, because in the case of water, we have non-bonding electrons near non-bonding electrons, which they definitely want to get away from each other. So they definitely go as far away from each other as possible, causing the hydrogens really to bend down and be bent in that sort of shape. So obviously, as we talked about, this is, you know, electron pairs, number of bonds, and memorization is a good thing to know on that. After we talked about geometry, we got into molecular polarity. And with molecular polarity, when we have diatomic molecules, that is the only place where both bond polarity and molecular polarity are the same. So when you have something like HF, this is a polar bond, which we could represent with that dipole arrow, where the arrow points to the more negative side. This guy is more positive. And because that HF bond is polar based on electronegativity, and because it is the only bond present, this would also be a polar molecule. And if we had our 2 Fs here, this is going to be a nonpolar bond. Going to have equal sharing of electrons. And basically, because that's the only bond that's present, we will end up with a nonpolar molecule as well. So the one place where bond polarity, which is where you use for your difference in electronegativity, and molecular polarity are the same, is in this situation where you have basically diatomic molecules. When you have 3 or more atoms, you have to look at 2 things. You have to look at, is there polar bonds? And if the answer is yes, you also have to look at the molecular geometry as well. So remember, we looked at, I think, carbon dioxide, which is a good example of, yes, it definitely has polar bonds, but because the geometry here is linear, they actually will cancel each other out. And this will be a non-polar molecule because of that, because of its linear geometry here. As opposed to something like water, which has bent or V-shaped, also has polar bonds. And because of its geometry, they actually will add to each other and create this dipole moment, right? Which is what happens in polar molecules. They have a dipole moment, and it would be a polar molecule. We talked about a pretty quick way you can determine molecular polarity by really just looking at your Lewis structures, and it really boils down to whether or not there are dots or no dots basically on the central atom. If you have no dots on the central atom and everything's the same on the outside, it's probably going to be nonpolar. If you have no dots on the central atom and everything on the outside is different atoms on the outside, it probably will be polar. If you have dots and everything is the same atom on the outside or element on the outside, it will be polar. So those are really quick ways you can kind of look at it and determine polarity, whether or not there's dots, and are everything the same on the outside or different on the outside. There are 2 exceptions that can have dots and be nonpolar, and those are the expanded octets. That's the expanded octet linear geometry, where you have basically this happening with somebody in the middle there. Again, because it's linear, is the same, it will end up being nonpolar. And also square planar, where you have something like this. Also expanded octet. I'll draw it sort of like that. But it makes that square planar. And again, if they're all the same, because they're in a square, they're going to cancel each other out. So those are two exceptions where you can't have dots on the central atom and still have a non-polar molecule. Question on that there. Then we got into hybridization. And hybridization is the idea that helps us understand, really a bonding model, helps us understand what we see, sort of the geometries that we do see in Lewis structures. And this is really the hybridization of basically atomic orbitals. So we take our atomic orbitals, like our S, our P, and our D, and we hybridize them together and make these hybrid orbitals. They end up being the same shape, they end up being the same energy. It creates for better bonding and everything occurring. So for example, if we, they are tied to geometry. So linear electron pair geometry. Linear electron pair geometry is SP. Trigonal planar is SP2, tetrahedral is SP3, our electron pair geometry. Our expanded as well, trigonal bipyramidal, SP3D, and our octahedral, SP3D2. Remember, you literally can just mark off what you got going on in terms of bonds, and it'll give you the correct sort of hybridization. So if we looked at something like CO2, and again, if we applied hybridization to the carbon, it basically has two electron pairs. So that's 1 and 2. So this is SP hybridized. If we looked at this guy we drew earlier, the nitrogen, it has 1, 2, 3, 4 electron pairs. So 1, 2, 3, 4. The nitrogen there would be SP3. So you could literally just sort of mark it off. Again, double bonds and triple bonds are counted as only one as well. So you do it just like you would do geometry. So you can apply hybridization to any element except for hydrogen. Usually it could also be outside elements you could apply hybridization to. We also talked about types of bonds, which are sigma bonds and pi bonds. Remember that pi bonds are a result of unhybridized p orbitals that basically overlap sideways above and beyond the plane of the bond. Sigma are more straight on, head on sort of overlap that occurs. So when we related this to the different types of bonds that we see, a single bond is really like a sigma bond. A double bond is made up of a sigma bond and a pi bond, and a triple bond is made up of a sigma bond and 2 pi bonds. So that is the relationship there that we talked about there. Any questions on that there? Yeah. Then I think that was pretty much what was in that chapter. Then we got into some calculations in chapter 5, which was about our grams to moles, our moles to grams, and our Avogadro's number. Remember that the molar mass is what we use to do that conversion, and we get that from the periodic table. And something like hydrogen, it is 1.008 grams per mole. We use that as a conversion factor to go from grams to moles. Again, if we have moles, we would multiply by the molar mass, and that would give you grams. And if we had grams, we would divide by it. That would get you moles. We also had Avogadro's number, which is 1 mole of anything is 6.022 times 10 to the 23. These could be atoms, these could be molecules. It is Avogadro's number that we use to go from basically moles to atoms, our molecules, and back. We talked about in this chapter, obviously, besides doing these sort of calculations, we talked about 2 different types of formulas, which is the empirical formula and the molecular formula. And remember, the molecular formula tells us exactly what's present. Empirical formula tells us the simplest ratio of what's present. And if you had an empirical formula of C2H6, that's the same as 2 carbons for every 6 hydrogens. That's the same as 1 carbon for every 3 hydrogens. The empirical formula would be CH3. We also talked about how to calculate the empirical formula. And if you're given the information like percent composition by mass, which reminds you is the grams of the element you're interested in divided by the molar mass of the compound times 100%. 50% composition by mass and assume 100 grams. And you basically would then take grams to moles of each of the elements that are present. Once you have the moles of each element, you then would divide by the smallest number of moles. And if you hit all whole numbers, that would be your empirical formula. So if you had 2 moles of A and 4 moles of B, and you divided everybody by the 2 moles, you would get 1 and you would get 2. Your empirical formula here would be AB2. If you do not get whole numbers, so if you don't get whole numbers, you get numbers that end like 0.33, 0.5, something like that. Remember, you need to multiply by a factor to get to a whole number. So maybe you need to multiply everybody by 2, everybody by 4, something like that to get to a whole number, to get to your empirical formula. To calculate the molecular formula, you basically need 3 things. You need the empirical formula. So either you have to calculate it or you need to be given it. You need the molar mass of the empirical formula. And you need the molar mass of the compound. And basically you take the molar mass of the compound, you divide it by the molar mass of the empirical formula, and that will give you a number. And that number is what you multiply the empirical formula by to get to the molecular formula. And again, that is the only place really where you can round. In this case, you don't really want to round unless it's really, really close to one another. If it's not, then you do need to use that factor. But usually on this situation here, you can do a little bit of rounding because it should be close to the whole number. Any questions on that there? Okay, that wraps up, I think, chapter 5.